Okay. Thank you, folks, for taking time to join in. I'm Shankar from Cisco, and today's topic is label switched multicast overview and applications. We just had a session, kind of went over, I guess the basics of both MLDP and point-to-multipoint TE. This session, I think, I've been sitting at the back and listening to the earlier session, but this specific session, I guess, is a little bit more involved, so feel free to raise questions or raise hands as you go through, as I go through the session, and it's, I would be actually covering the need for what is a label switched multicast, and I'll be covering the solutions, which is both the point-to-multipoint TE and MLDP, and then the OAM extensions to support the LSM. Obviously, that becomes a critical component for LSM when you're actually carrying multicast. What are the things that are being done as part of the OAM? Okay, and then also look at some of the applications. So if I take a pause for a second and ask, how many of you guys are service providers or enterprise guys? How many of you are service providers? And any of you guys are enterprise? Okay. So in a way, the session is actually applicable, both for larger enterprises and also, obviously it's for the service providers too. The scope of the presentation is obviously, as I just mentioned, I'm going to cover the motivations for the label switched multicast and go over the building blocks for both MLDP and point-to-multipoint TE LSP setups, okay? And then look at the applications. So what exactly is LSM? An LSM is actually it's an MPLS technology for both a point-to-multipoint and for multipoint-to-multipoint LSPs, and we actually build the trees using the labels, okay? What are the drivers for the LSM? So currently, most of the customers that any of the existing MPLS deployments that we have, for unicast is using labels, is it right? And then we are actually using for multicast regular IP routing. So now here is a requirement coming from, obviously, not only from service providers or for any of the larger enterprises and bigger customers, for a unified control plane that actually runs for both for unicast and multicast to have a single plane. And also that actually simplifies the core routers by removing the PIM. So you have your own mechanism for both using the point-to-multipoint and MLDP. You can actually have the core without the PIM, and some signaling mechanisms can be set up that can be built using those two protocols and have a common control plane for both unicast and multicast. The other bigger driver is actually coming from video content providers, and the video content wise, you have either you may have some form of a contribution networks, or you may have a secondary distribution or a distribution networks, in the sense if you have a contribution is any existing providers that where if you have a source feed which is coming from studios or sports stadiums and coming to a central repository, that's pretty much referring to the contribution. And once it comes in, then you go from that to a production houses where you take the video content, and then like could be television companies like NBCs of the world, and then they take the content and then they start distributing that content to the secondary distribution where you have cable MSOs or whatnot. And when you take that cable MSOs and give it to the consumers, that's the kind of the flow. So you have a contribution network, then you have a primary distribution, and then you have a secondary distribution. Okay? And there is a requirement right now, or there is a need, or there is kind of the market is shifting towards of the multicast to play, because all the video, multicast need to get replicated all the way to the consumers. And I guess in this particular example, point-to-multipoint TE is kind of taking a lead as compared to MLDP. So when I cover the applications, we'll go through some of the examples. And in a way, in terms of the real deployments, the deployments are still happening. In the sense it's at the infancy state for both MLDP or point-to-multipoint TE. As I just said, video is in one existing example where content providers are coming and asking, yeah, I got a specific requirement, do you have a solution for point-to-multipoint TE? This slide kind of captures the work at the standards. I try to summarize at a high level the MLDP, and then point-to-multipoint TE, and then LSM, OAM, and the VPLS. As part of the session, I'm going to focus on MLDP, and then obviously point-to-multipoint TE, and the OAM extensions to the LSM, okay? So the signaling options, as we just talked about it, the multicast LDP is a receiver initiated, and versus the point-to-multipoint TE is a source initiated. That's the main key difference. And the applicability, we kind of little bit talked about it, where MLDP is applicable versus where point-to-multipoint TE is applicable. Like if I'm a VPN customer, where if I have a default MDT, and then if I have, for example, multipoint to multipoint, then I may go with MLDP, is that right? And if I'm a video content, you can clearly kind of have, even though these things have been coming out, we're kind of seeing some kind of a trend, how the actual deployments are slowly happening, okay? So at a high level, the LSM architecture is actually, this is a good slide in a way, in the sense that it captures what it is. At the bottom, you have a LSM forwarding, which is a common forwarding for LSM. And then on top of it, you have the signaling protocols. And I have also bundled LSM OAM. And we did talk about a little bit about what is MLDP. I have subsequent slides to go in detail. And then point-to-multipoint TE. On top of it, the C multicast signaling, which is a customer multicast signaling. You may leverage BGP, or we have a pretty good deployments with the PIM, or we have a new thing which is coming up. It is still a DIETF draft, which is a port model, which is a PIM over reliable transport, which uses a TCP for PIM. So it's a very infancy state. But I just wanted to capture to reflect the current state of the LSM architecture, okay? And then on top of it, you have what you call as clients, and clients are services. Those could be, I just try to put at a high level some of the services. Could be IPv4 native, IPv4 MVPN, IPv6 native MVPN, and VPLS, okay? I can have IPv6, 6PE, 6VPE as another examples. So, but at a high level, in terms of the deployments, a lot of the deployments or existing deployments are currently in IPv4 space. IETF is proposing all kinds of possibilities, but when you actually get to the real deployments, you can only have finite number. You can't like simulate everything. So So let me pause for a second. Any questions? Because the next slide onwards, it kind of gets into the weeds in terms of building the concepts. But you guys, everybody's clear. What is the drivers, what it is, and what's the LSM architecture, okay? So I want to take a couple of minutes to introduce you guys to the terminology, because as I go through the rest of the presentation, I would be spending quite a bit of time, and we would be going through these terms together. So it's probably good to have it understand what they are. I guess we are clear on LSR, which is a term that has been already used in the MPLS world. And then ingress LSR is an LSR which is the source LSR where you initiate or you actually start the LSP, is that right? And then that's kind of, you may call as ingress or a source or a root node. If somebody says these three terms together, they kind of at a high level, one and the same. The other one is egress LSR. Egress LSR is the same as similar to leaf LSR, or where you have a receivers. So if you have a receiver / a leaf or egress, they are one and the same. Then the point to point. See, every time I'm trying to say here, I'm trying to make sure that I say P2P or P2MP, and I know this topic is on a point to multi-point, but I guess a point to point is like, for example, in the previous session, as we have seen, setting up a TE LSP between a head-end node and a tail-end node. It's an LSP between two nodes. Point to multi-point is where you have one unique ingress LSR to going to multiple egress. That means you have a root and going to branches. Think of like an upside down tree. Okay? The multi-point to multi-point is where the role of the node or the router or the device, in this case, whatever the case may be, or the word you want to pick up, has acting both as an ingress and egress. Then when I set up those LSP, as we just talked a little bit just a while back, MBPN, default MDT, where PE to PE, PE to PE is MP to MP, which is a multi-point to multi-point. And then MP-LSP is any type of a multi-point LSP, which is at the bottom. So the LSR and LSP, and the next slide is about the tree. Okay, once you have these LSPs, then you build a tree, and a point-to-point LSP becomes a point-to-multi-point tree. And then we talked the little bit about ingress or the egress. So in terms of the label distribution, an upstream label distribution is called an egress towards the ingress. That means a receiver towards the source. The other way is source towards the egress is the downstream. That means the source sending all the labels down. The branch LSR is an LSR which is a P node in the middle, which is replicating the traffic, which is a branch. And if it confuses anymore, we've got two more terms to go through, but I guess we are done with, at least hopefully, with the terminology. The bud LSR and a leaf LSR. I think a leaf, we are clear, I guess. Leaf is the node which is the one which is egress. A bud is a leaf along with, it may have some downstream nodes, LSRs. That's all it is. So let's take a quick kind of a terminology mapping. I thought it may, pictures kind of convey more than 1,000 words. So we have an ingress, source, root node. I'm using synonymously for clarity. Okay. And then we have an egress, which is the receiver, right, or the leaf node. And then you have a branch LSR. So all in this example is you have an LSP that is set up from a PE1 to, for example, PE3 or PE4. Then P1 acts as a branch LSR and replicates to PE3. I'm having a trouble with this laser pointer, but yeah, to PE3, PE4, and a PE2. I think we are clear on that particular picture. Let's move on to the picture to the right of it, I guess. On this one, now PE5 and PE6, for example, wants to join the tree. Is that right? Maybe they may have some interested receivers. They got a PIM join, whatever the case may be. And now, when a source sets up the LSP, when it comes, like in this example, like a P2 and a P3 become the branch LSRs. And the bottom picture, I try to simulate an example to explain the bud LSR. Okay, and don't get hung up on the receiver is directly connected to PE. Even in my examples as I go through, if you see a receiver, think of like you have some kind of a PIM domain, some kind of a PIM join coming in. It's just for clarity and maybe just to simplify. I attached the receiver to the PE node, okay? Any questions on the terminology mapping? We are good? Good, good, okay. Is the pace is good? So now let's cover what is MLDP, and we know what it is in the sense of the acronyms it stands for, and we little bit touched on one thing, that MLDP is label service is actually receiver driven, which is egress. That the labels are distributed from the leaves towards the root. The key thing is when MLDP builds the tree, it does not depend upon the underlying PIM or any other mechanisms to build the tree. So you do not require any other protocol, underlying protocol running to build the tree. So as we go through the subsequent slides, we will see how it actually does it. And it is a receiver driven, and the path selection is based upon the root node address. The root node address, we kind of touched a little bit on it, which is nothing but an ingress LSR. And that root node address, a leaf node or an egress node, does it or picks it up based upon some kind of a static routing or some form of a BGP next hop reachability. So it knows how to initiate the LSP and reach the ingress. And in terms of the label allocation, it is downstream on demand. And I think there was a question earlier, downstream on demand or unsolicited downstream. The way the labels get distributed usually is when you have the FEC element, which I will go through, and then it will allocate the label towards the upstream. And the key thing is there is no PHP, no penultimate hop popping. That means the labels have to be preserved all the way to the end. And in terms of the signaling architecture actually supports in-band signaling or overlay signaling. Overlay signaling, or you may call as out-band signaling, out of band. And as we see some examples later, which of the applications would be using in-band and what would be the other application maybe using some form of out-of-band, okay? Using that signaling, you set up the LSP. This picture kind of conveys at a very high level question.
Just a quick question. So you said that it's from the leaf towards the source.
Yep.
Is that basically just turning on ordered rather than independent control mode, or is there another mechanism to do that on top of that?
It's independent ordered. Yep.
It's ordered, right?
Yep.
Okay.
Let me also spend some time on this. I think we may get some better idea on this particular picture in terms of how the signaling kind of works. Okay, so as we see here in this particular picture, I would like to break this picture into two parts, okay? One part is a PIM domain, and the other part is an MPLS core domain. So the PIM domain is running at the edges of the network, okay? Where, PIM enable is either at the, right-hand side edge or the left-hand side edge, okay? Kind of the PIM domain. And then you have an MPLS core, which is a PIM-free zone. And assume that you may have an interested receiver on the right-hand side that sends a PIM join, trickles all the way towards the CE to the egress, okay? And then you use some kind of a signaling, which is in-band or overlay method, and signal all the way to the ingress. And then that kind of example, I kind of gave a little bit, hint, which is a BGP or some form of a static routing, that you know the route, and then you signal all the way to the route, and then when the route gets the packet, it strips it off and then knows that it is for it, and it is for the same S, G, that it is the interested sources, and then it starts forwarding the traffic towards the receivers. Kind of clear? A little bit clear? The example here is, this example is a point to multi-point, and we are talking MLDP. And MLDP supports both point-to-point and multi-point to multi-point. So if you guys, like watching, oh, Shankar, hey, how come is there only one ingress, is it right? I may have several sources if it's a multi-point to multi-point. That would be a good question, and it's the particular topology here captures explaining the one example, which is point to multi-point, okay? And it would be the same mechanism if I have different sources too. In terms of the traffic coming from the egress towards the ingress is upstream, and from ingress towards the egress is the downstream, that is away from the route. So as part of this, the LDP protocol has been extended, and I didn't want to go into gory details, but at a very high level, you have an initialization message, which is part of the LDP. Within the initialization message, you have a capabilities parameter, and within the capabilities parameter, you have the capabilities that are advertised to tell your peer. And for example, LDP capabilities, LDP graceful restart is one capability. This is exactly like that. Within the capabilities, now I'm going to advertise like whether I have a point to multi-point capability or multi-point to multi-point, and then MBB, which is make before break. All it is if I set up an LSP towards the route, and if for some reason, if that LSP has been changed, it could have changed because my next stop has gone down or some peer has gone down, I may have to recompute a different path. Then what I need to do, I need to go to the different path, but I can't tear down the existing LSP and move the traffic appropriately, make before break. Okay, but so these are the three capabilities are advertised to my peer as part of whether if to the peer to say, hey, I'm capable of doing these things. Once I'm done, then if for some reason the peer is not capable, then obviously they can't exchange this particular LDP extension. So other than that, if they are capable, then if something happens when the labels are coming, mapping, then they will exchange. So the labels are exchanged once the capability has been exchanged is via the label map message. That's a second extension. As part of the label map message, you have a FEC element. Is that right? Forward equivalency classes. Within the FEC element, you have a new FEC element that they have defined, and then that element, along with the label TLV, which is nothing but the label, which carries, identifies uniquely that particular stream for that particular point-to-multipoint LSP. So the FEC element types are point-to-multipoint FEC, multipoint-to-multipoint upstream, and then multipoint-to-multipoint downstream. So the FEC element obviously will consist of a root node address to identify to which route that I'm going to, along with the opaque value. The opaque value is what type of application that I'm carrying, whether I'm carrying MBPN or if I'm carrying a PIM SSM transit, or it could be S, G, whatever that could be. It's just a value field that is part of it will be carried as part of the FEC element. So the combination of both the root node address and the opaque value uniquely identifies each unique LSP. So you have an initialization message, which we talked about it, and then after that we have a label. And as part of the label, the FEC, and within the FEC you have the opaque value. That's pretty much, okay? And so that is the root node address and the opaque value. Those two nodes uniquely identify, which is part of the FEC element. We talked a little bit about the root node address that is obviously picked by the egress router, automatically derived from the BGP next stop, are statically configured, and the root node address is obviously used to build the MPLSP. So as I said, the opaque values are the applications that are question. No, but I think the question is in MLDP, the receiver to the source could be picking up one path, versus from the source towards the receiver, it could have picked up a different path. Actually, the thing is, based upon the root node address, the egress router picks based upon whether static or BGP knows the next stop address, and sends the request all the way to the source, and matches based upon the FEC element. And then yeah, it could be asymmetric because the source could be may pick a different path based upon its reachability towards the egress nodes.
So you're not really following the exact IGP path that the forward direction is forward traffic. Because you have to set it on the path that the receiver has set up, rather than the path that you would have chosen if you had computed the path using IGP.
It's not necessary. Well, you are actually picking up based upon your source node addresses, right? Based upon your IGP next stop, and I'm thinking it loud too. So it would pick the path, and but the labels are it would be the same, because based upon the label allocation, which is unsolicited, it's like a normal paradigm, is it right? Like unicast example, it's the same. The way LDP works, the regular for unicast traffic, it is exactly the same thing. It is just that it has a new FEC element. So I think that thing won't change whether it is a multicast versus a unicast. So whatever the applicability of the unicast would remain the same. So
The only difference is that it's not unsolicited over here, it's only one.
it would,
Maybe everyone's, setting up their state for the same spec.
it depends upon, is it right? Like, but again, it could be unsolicited if I have an interested receiver. If I'm the receiver, if I receive a PIM join, then I build the LSP. Then I may tell my upstream neighbor, which is my P node, here is the LSP because I got a receiver who wants to join this S, G entry. So it is applicable for both. Okay? So the opaque value is each MP-LSP, as I said, is identified by the unique opaque value, and the opaque values we kind of like PIM SSM transit or MVPN or any of these examples. So I just try to highlight some of the applications: IPv6, MVPN, PIM. And the IETF draft also proposes direct MDT. I just put it up there, so, but I'm not sure how many vendors actually support that, okay? And let's spend a minute or so from here. This concept-wise is a little tricky here. I'll try to do a good job, hopefully, on the MLDP signaling. So the signaling obviously provides two functions: to discover the FEC and to assign the multicast flow, okay? So to do that, you got two signaling methods, which is the in-band signaling and the overlay, which is called out-of-band. And for in-band, the existing receiver has all the necessary information to build the request and set up the LSP. So what all it does is the egress routers use, obviously they use kind of the algorithm based upon the opaque value and the multicast stream, and within based upon the PIM join, you may have S, G entry and the next stop and all that. That it includes all that as part of the packet, and then it initiates using the FEC element. Okay? Whereas the out-of-band signaling is where an example for out-of-band would be MVPN, is it right? Or IPv4 send label option. I may have a MPLS core, and then I'm just using, just the MPLS with no BGP. IPv4 BGP IPS with IPv4 send label would be another example for out-of-band signaling. So an in-band would be, for example, as I just said, as the caveat with these diagrams, as I said, anytime you have a receiver, there is a PIM domain. Just take that as a thing. And then if there is a PIM join comes in, that PIM, based upon the PIM join, the PE, which is the egress / the receiver, initiates the in-band signal towards the root using the source address and the root node, and based upon what are the opaque value, which is S, G. Okay? And then when PE receives it, it knows that I have an interested source, and then sets up the LSP and forwards the traffic. Whereas with out-of-band, where even actually in band, if I have another set of traffic coming in, and then I have to initiate unique, path back from the receiver to the source. If I want to do some kind of an aggregation, like a regular MPLS VPNs, is out of band, is it right? Like based upon our, VPN, VRF, multiple prefixes are coming, is it right? And then they all map to one egress PE label. So that one label maps and then do an aggregate lookup. That's an example of an out of band. And the other example that I have given you guys is IPv4 BGP free core, IPv4 send label option. So where you just run LDP and the P nodes just run LDP based upon the label they switch the packet. and then you have end-to-end reachability. So let's take a look at the label in terms of the point to multi-point basic operation. I intentionally did not put in a lot of animation, guys, and I didn't want to confuse to myself and to the audience, because sometimes, too many arrows flying back and forth. But let's take a minute. I think it's not that complicated, this particular picture. It's a very simple picture to understand the concept. You may have a receiver who wants to join in. Is that right? You got two nodes, R1 and R2, which are receivers. They got a PIM join. Now they got to, they need to find out, where is the source. Is that right? Based upon some form of a in-band or out-of-band, they know the route. Is that right? So what they do? They use the label mapping, which we talked about it. Within the label mapping, you have a FEC element. Is that right? So that FEC element identifies whether it's a point to multi-point downstream or a multi-point to multi-point upstream or downstream. So that's what it uses. And then FEC element, and then the root node address, it identifies, as I just said, based upon some form of BGP next stop, and it signals to to their upstream. And R3 receives it, and it signals the same towards the root. We are so far clear? So you may ask the question, hey, how come it's 200 here and it's same 200 here? Which is a FEC element. Based upon the S comma G, which is that R2 or R1 they receive, going to the same route means the FEC element would be the same. That means, I'm getting the same S comma G to the same source. So they derive at the same value. Anything else? I think that kind of covers at a high level going from kind of the upstream, going from the leaf towards the source or the root. Based upon that, when the actual traffic is coming, is it right, from the source, then the root actually uses the label that has been given by the R3, which label 3 was given by R3 towards R4 to say, hey, R4, when you do send the traffic to me, use that label. The same thing here, R2 says, use the label 2 when you send the traffic towards me, to R3, okay? Using the same, using those previous example, then R4 would be using label 3 towards R3, and R3 would be using label 2 towards R2, and R3 also would be using label 1 towards R1. So far, is kind of clear enough, I guess, guys? Good? Okay. So that's kind of the fact, the R3, incoming interface, FAC 200 downstream, label 1, label 2, forward versus the other one is assign, A for assign. So if you kind of get into your order and if you do it in the appropriate show commands, you kind of see, and I think the previous session had some show commands. So if this confuses you guys or it's a little complicated, the next one is even more complicated. Which is multi-point to multi-point. You kind of, your head spins, or at least my head started spinning several times. So hopefully we'll pause for a minute and we'll take our appropriate breaks and understand. But I think I did not cover the make before break intentionally. That's another beast by itself, because again you have to have the appropriate topology to understand. But I do have a multi-point to multi-point. So let's go through that. So when there in the multi-point to multi-point, we have the multi-point to multi-point downstream and upstream. So that multi-point to multi-point downstream is exactly the same as this point to multi-point downstream, okay? So that way 50% job is done easy. So what I did is I kind of color coded. So in this picture, even though it's a lot of dents, but let's, for a second, any red color is exactly the same as the previous example, which is the point to multi-point downstream. So the only caveat is that instead of using a point to multi-point downstream, the FEC element, in the FEC element, they would be using multi-point to multi-point. That's the only difference. Other than that, if there is a PIM join, the same FEC element, the root node and the root and everything is the same. Oh, there is a question. Okay.
So you got label L3 used in both upper left-hand label mappings.
Oh, okay. That's a very yeah. Go ahead.
Are those actually supposed to be the same, or is one L5? I didn't see L5.
Yeah. So the question, I think, it's a very good observation, and like a label 3, I think it depends, is it right? If I have an interface space, interface specific label space, what's a platform, so it doesn't matter. You know, I can have a label 5 and it's a local significant. That's, you know, I think, you clear? Okay, cool. In terms of the concept, I looked at it, you know, yeah, for the presentation it may confuse, but think of like it's a unique label, okay? Okay, so where are we? We are clear on that the multi-point to multi-point downstream, which is the same as the previous example, other than that, you know, that it would be advertising MP to MP, okay? And at the same time, you may have sources somewhere also here, like in this example, here too. So then what does R4, this is the green link, that is the R4 would be using multi-point to multi-point upstream and would be saying, hey, R3 use this label to send it to me, which in this case is like a label 6. Okay, the same example here, R3 would towards R2, R3 towards R1. Those are the other, these 3 boxes here. So far, I think we are okay. We are not lost, is it right? Okay, question. Exactly. So that's a good question. So the question is, yeah, so that's a good question. And so I didn't want to complicate the slide, but here this example is capturing one S comma G, okay? And so if any, you know, I intentionally didn't bring it up, the whole PIM multicast discussion. It is, if anybody is clear on how PIM biter works, that's exactly this is how it is. So anybody knows how PIM biter works? So then this multi-point to multi-point is exactly where, you know, the same concept. So here in this particular topology, I'm just, you know, you pick a root, is it right? And then I'm just trying to illustrate in terms of the example of the downstream and the upstream label allocation for multi-point to multi-point, okay? So let's spend a couple of minutes, a little bit of animation, but it's not that much. So in terms of that, this is the label replication for downstream. So that means when the traffic is coming from R4 down, and we are kind of focusing on R3, how does R3 does the label replication, is that right? And this is as we went over on the point to multi-point example. Like, so label 3 downstream maps to label 2 downstream and maps to label 1 on R1, okay? This is, so far we are good to go. What kind of gets a little bit tricky or difficult to follow is the upstream now. And again, we are looking at the same node, which is the R3, okay? So that means if in kind of an MVPN, whatever the case may be for some kind of a signaling. Now, this example is R3 upstream table from a serial 1 example, right? So what do I do? So the upstream label, which is the label that is given by R3 towards R2, R2 will be using, and we'll be using upstream label towards the root and downstream label towards the leaf. So at a high level, in terms of the label allocation for upstream, downstream, from multi-point to multi-point is, I can kind of simplify this and say, anytime when the traffic is going towards the root is upstream. That means if there is a node which is a transit node in the middle, and if it needs to send the traffic towards the root, it would be using upstream. And if it needs to send to any of the receivers, it would be using downstream. Kind of just to little bit put the concept or kind of clarify ourselves together. The same applicable here. When R1 sends anything, R3 would be using upstream towards the root and downstream towards the R2. So if you guys followed this, I think that's all I have here, both on the point to multi-point and multi-point to multi-point signaling. As I just said, make before break is another example on its own. It will be years before, a couple of years before actual deployments where those optimizations and the TLVs that we have to talk, okay? So that's that thing that I have here on MLDP, I believe so. So any questions at a high level, what we have covered, and on MLDP?
What's the status of all this? Is it work in progress or is it almost done?
Yeah, that's a good question. So what's the status? So the status of the MLDP draft, it's actually become an RFC. So in terms of the vendor support, I believe the different vendors have some form of a support that it is coming, or they have some plans on the roadmap. Okay?
But I can't go and download it, just operate the software and then run it.
Since I work for Cisco, I can speak for Cisco. I believe in XR we have the support coming, I think, real soon, like 4.0, 4.1, but guys, don't hold me on it, okay? But if it is point to multi-point TE, I believe 3.9 XR has the support already. Question?
So, I guess we were just talking, ASM, not really, any solution. I'm not real clear how that breaks down unless you, I guess you have static RP mapping or something like that, so you would say, oh yeah, RP is the root, and that's how this all works.
Yeah, so we have to see, in a way, to be honest with you guys, in terms of the real deployments, there aren't any, So there will be a lot of lessons learned, I guess, and hopefully I'll come back maybe in about a year back and kind of, share, this is how it's been getting deployed. At this time, we have a good starting deployments on the point to multi-point. TE, I know I've been working on one provider already where we have one getting rolled into production. On MVPN, we will have to see. So, okay. So does it, at least at a high level, guys, it helps what it is, the facts, and then the tree types, and then point to multi-point, multi-point to multi-point, okay? And let's, given the time, let's give some due justification to the other one too, I guess. And then I have some OAMs, so on, okay? The point to multi-point TE is kind of the opposite of what we actually talked so far. This is obviously is a source initiated. That is the ingress initiated towards the egress, okay? And supports the traffic engineering, the explicit routing, fast reroute, bandwidth reservation, all the mechanisms. So any of you guys have a TE in your network? Yeah, so yeah, it should be easy to follow. So this is the other terminology slide, which is the difference between, or not the difference, actually what is, in addition to what I have covered before, or to be more clear, I guess, is specific to the point to multi-point TE. And a sub-LSP, the source to leaf sub-LSP, and S to L, drafting, pruning. Again, hey, bunch of multicast words, so we should be clear, is it right? So, but I think at a high level, sub and source to leaf, I'll cover in a picture. And then crossover, remerge, I will cover what they are. I have some pictures later on, but hopefully that will explain, okay? This at a high level captures similar to what we have covered for MLDP. What are the things that are done for multi-point TE? The existing session object has been extended, with the new elements, I guess. And then the same thing with the sender template. And I'm not expecting you guys to memorize, I don't remember, but I wanted to capture at a high level that the two existing objects have been extended, okay? And they have added a new object, which is the S to L sub-LSP, that only has the destination. I want you to get this out of this slide, and then I think we're good to go, is when we have the existing traffic engineering point-to-point, the session object actually has a destination because you have one ingress, one egress, that's it. So the session object has, as part of the path message, you have that, the destination. But in the point to multi-point, you are not going to one destination. You may have egresses or leaves, multiple guys. So they decoupled it and they uniquely created another object, that's it. But to identify the LSP, they have added the ID, a new unique ID, point to multi-point ID. So if you put a sniffer, you will see it, kind of a thing. Yeah, these are new things exactly to the session object, yeah, the three elements. Well, when I said the destination was there, that is for the existing point-to-point, yeah. So if it is a point to multi-point LSP, then the destination is not there in the session object. And then that destination uniquely identified by the S2L sub-object. So that means if I have, if I'm the source, if I'm going to node A, if I'm going to node B or a node C, so node A is 1.1.1.1, 2.2.2, or 3.3.3. Those 1.1.1 would be in that, or 2.2.2. That would be the destination address. That's a good question. So hold on to it if I don't answer it, yeah. But I want to build the concept. Yeah, that's a good question. Very clear, is it right? I didn't want to drill down, but I kind of bringing some of the differences of the existing point-to-point to point-to-multipoint. So in a way, so given a point-to-multipoint LSP, so these are the objects that uniquely are the, I'm using the word loosely to objects or elements or what, these 5 elements, uniquely identified, which is nothing but the session, the sender template. I wish I had, actually I have, I have, configs but it's a neutral forums. I didn't want to give you guys a Cisco configs, but you can actually clearly see, even if you put a sniffer or a debug or anything, So given that my terminology section where I kind of covered that the source to leaf, so given each one is like each dotted line or whatever the color coded, that's why I kind of made the node at the bottom, like each one is like a sub LSP. So all those sub LSPs, again, is answering the question that got raised. Is part of the same path message, or is individual path messages? That's implementation. The IETF draft says you can do whatever you want, because even if you do what I mean by whatever you can do means I can signal a path message, but that path message has a point to multi-point ID that identifies, glues it together. Answered? Okay. And sub LSP we covered, and the crossover. This is other, if you look at that, what are the RFC number that I put it into the slide, guys, they kind of talk about this. Trust me, there isn't any pictures anywhere, and I got to kind of spend some time and come up, and so when the sub LSP, for example, if a PE1 is setting up an LSP to PE2, and then it kind of goes through like kind of the upper path. The key thing is, as I said, here is coming on an ingress interface and going out on output or outgoing, whatever the different interface. And then if I have another LSP coming on one ingress and going on another egress interface, that's a crossover. So coming on one input and going on a different output. What would be the examples? What are the applicabilities, or what are the applications? Like if I have some kind of optical gear, wavelength thing where it has some requirement where that wavelength has to go on this interface and needs to go on egress on a different interface could be one example. But as I said, we have to see. But that's the guys at the IETF said, okay, this is what the definition, okay? And this is the one which is a remerge, which we should not see in the networks. Is the same example as the previous topology where, again, took the two LSPs coming on a two different input interfaces on a P3. Like in this example, assume the PE1 sets up an LSP first to PE3. And now then it got whatever the thing, it may need to set up another LSP towards a PE2. Then it is actually going on the same outbound interface, egress interface. Then, the packet duplication happens because I got to duplicate the packets. So then what we do is, we send a path error message as part of the, the RSVP and send back. An example could be user error, like I got an explicit LSP setup, point to multi-point, and then I may have another explicit LSP setup. If it is a dynamic path option, yeah. We are the right path, exactly. The question is, if I have an explicit path option, that particular LSP won't be able to set up, won't be able to be set up. If I have a dynamic path option, routing converges or whatever the criteria may be, and then I'll pick up the right path. So what did we cover? We covered source to leaf, sub LSPs, the remerge, the crossover. And then grafting, the same as the multicast terminology, where when a PE3 wants to join the existing point to multi-point LSP, means is the where that's basically called as a grafting, adding to the existing LSP. So the two mechanisms where a grafting can happen. Either you can add to the existing point-to-point, point-to-multi-point LSP by refreshing the entire path message, or uniquely sending, the path message, which is kind of more of an incremental update. It's again implementation specific, how, whether it's the same path message where you refresh it, or do you initiate a new path message. The pruning is, yeah, go ahead, the question.
Yeah, I just want to make sure I'm straight. So all that's said from the paper, this is a TV, and it's on the receiver, a PIM message, PIM join, from the, whatever the C routers, the that connection, the scenario kick off.
So if I have a slide later on after I'm done, I guess, with the pruning, and I will go through how kind of the signaling works. So if it still doesn't answer, bug me, okay? The pruning is where, hey, I want to, I don't have any more receivers. I don't want to be the part of the tree. Again, here, two methods, I guess, the, implicit tier or explicit tier. Implicit tier is existing path message where you include all the receivers without the guy and send it. That's implicit. Explicit, which is a path tier message saying, I don't want to be part of the tree. The applicability of the point to multi-point, the idea is, as I kind of went over at the beginning of the video content providers and the distribution, the contribution and all that, is where I have the limited, I'm using the word carefully here, a limited set of sources. It could be one source or a multiple, not that many. And then all I got to do is just replicate the traffic downstream. So the egress, like here, getting off the tree is very rare, because once you have the ingress sending all the traffic to the egress, they're just getting it. Versus the opposite is true, where for MLDP, if you have a lot of receivers joining and going, coming, because they're all receiver, initiated. That's where more applicability. So if the states are changing constantly, the receivers are coming and moving in like MVPN environment, whatever the case may be, then MLDP is more applicable. And so how does it, at a high level, it actually works? So you may have a PIM join. Actually, this is trying to answer the earlier question. So I'll have two slides. Hopefully, I will try to answer, okay? PIM join comes in, and then here is an example of out-of-band signaling. As I just said, use some form of a static or a BGP. So if you take a Cisco router, and if you're configuring an XR, you configure BGP, and then you put the neighbor address family, boom, you're done. So it knows. It knows whom. They have it between them, like to the root node, the source node. And then, based upon that, now the root node has the information to initiate. So, guys, again, I didn't do intentionally any animation. Any of these kind of bluish line. So the path message will be initiated from the source or from the root towards the leaf or the egress, and then the reserve message. So the normal mechanism of the path message and the reserve message are used with the extensions, for the lack of a better word, as I mentioned, for the things that are done to the session, object or sender template, and then we talked about the new object that they got, which is a S2L sub-LSP object, which includes the destination address. Will be signaled as part of the path message, and when the reserve message comes, it includes the reserve message label. Clear a little bit? I didn't want to go too deep, but it is already deep enough, I guess, but hopefully it explains the concepts. So that kind of concludes both the MLDP and the point-to-multipoint TE. And I'm going to go to the next section, which is the OAM extensions for the support of LSM. And obviously, OAM becomes maybe, I don't want to say afterthought, but IETF is actually already working on several extensions to make sure these LSPs, which are multicast, like, going from, any to any, somewhere for the operators to have some kind of a way to detect. So there are some extensions done to the existing LSP ping, which is for unicast, which is now is called multicast LSP ping. So we will go through that. And now let me warn you guys that, I can't help it. Any of this particular section is a lot of animation, but it's not that much, but it kind of explains the concepts. And then proxy LSP ping. So for multicast, what happens is, somebody will be calling, saying, guys, I am not getting the video stream. I'm not getting my channel, whatever they call. And then if I'm the operator, I need to identify the problem where it is. So with the LSP ping, we will see what happens. And the proxy LSP ping is kind of more of an optimization to how you actually trace or ping the multicast tree. And none of them actually are the drafts yet. What I mean is the RFCs yet. Most of them are IETF drafts. And some of them still, some of them are vendors like Juniper, Cisco, and all, co-authored by a bunch of guys. So it's at the IETF. So, and then the last one is the multicast connectivity verification, for abbreviation, we just say CV, where we will see how BFD gets used, but again, that's the proposal, okay? So if anybody is familiar with the unicast LSP ping, exactly the same. What does the unicast LSP ping uses? Echo request, echo reply, is it right? Same mechanisms. I guess my animation is coming. Ooh, okay. So that means here is a source node, which is sending, towards the tree. If I kind of go back, I can't go. Oh, it's already did the animation. Okay. Yeah, the source to the leaves. Okay, and then it sends the echo request, as the red line stands for echo request, and as we see those animation of kind of whatever the lines came in, or the echo reply. What's the problem with that? Let me quantify my question. What's the problem on R1? Is it right? Exactly. Yeah, so R1 can get overwhelmed, is it right? It may get a lot of responses because this is, point to multipoint. It may miss, whatever the case may be. So what they did is, when I said they here, the IETF, the draft, they proposed two optimizations to the multicast LSP ping. One is, I guess, the randomization, which means, don't respond back to me right away, kind of delay it, so that way I have breathing room so that I can get all the responses. And then also the other one they mentioned was a scoping parameter. Means, scope is like 2, 3, whatever, how far you want to go down the tree, so you don't have to go. That goes back to my question. Somebody's calling, hey, I can't get the video stream, so at least you can go to that part of the tree and start doing it. So again, this is one idea, one draft that's been proposed. Okay, and I kind of have at the bottom that the draft too. So if anybody's interested. Intentional, I didn't put all the TLVs guys here. I just trying to get the concepts across. And then the proxy ping motivation is again, this is the kind of the additional enhancements to the multicast LSP ping. is to reduce the number of replies, right? And the scoping can be limited, and let's take an example of the picture that helps the concept. Proxy words gives you guys the hint, where the color coding here, the purplish and whatever that color. So here the ingress node initiates the proxy ping towards the downstream, and then as part of the proxy ping, the ingress guy is going to say, please initiate your LSP ping downstream. Any responses that are coming, they should come to me directly. As part of it, this guy, when he sends a proxy ping, he may send a proxy reply and initiates to the downstream. So you're actually limiting the number of messages, is it right? And it's more of a scalability. And actually, one of our Cisco DSC actually is a co-author on this draft. So. Clear, guys? A little bit clear? Okay. And this example is for the point to multi-point TE using the proxy ping. This actually is similar to the previous example because the ingress node is the one which is the one that initiates the LSP, and as part of it, you do the proxy ping. And how actually proxy ping is more applicable in this example. As you can see, I don't know how you guys, if you have watched it, only a part of the tree has been traced with the proxy ping, and not the entire tree, because you can detect the fault location faster. And also the rest of the tree is kept unique. Whereas if I take MLDP, and with MLDP what it is the receiver who is initiating, and it has to go all the way to the root. And so that means as part of the proxy ping, the egress router sends, in the previous guys you see that proxy ping, and telling to its upstream router, initiate the ping towards me, or a trace, whatever that thing may be. And as part of the reply, the egress router will include its upstream egress router towards the receiver. And then when the receiver, now it sends a proxy ping, it increases the TTL, sends it more towards, closer to the source. The concepts very clear, guys? We're good to go? Okay. Enough of those animations. I got one more animation slide. That is this one, which is the connectivity verification. A connectivity verification would be where, for example, an example would be existing deployments of any of, like financials or any of the banking or stock trading, where, currently you typically have 2 feeds, right? As the picture here depicts, you have 2 feeds. And one would typically be the primary, and another one would be a secondary. And primary goes, and if the primary goes down, you want to switch to the secondary as soon as you can. And how does, in the multicast, if I'm doing, how fast I can switch? So what they did is, as part of the connectivity verification draft, they proposed the BFD. So using LSP ping. So what they do is, as part of the LSP ping, they bootstrap the BFD session, and the BFD session is going to have some parameters and say, hey, I'm going to send you heartbeat X amount, for X period, X time interval, whatever. I'm just really sending it to you. And then if within that interval, if I'm the receiver, if I don't receive it, then I'm going to take an appropriate action to switch the traffic, whatever that case may be, or notify my application. But the concept is to send it downstream, and then the downstreams this is unidirectional, and then the receivers get it, and if they don't get it in a timely fashion, they will take the appropriate action. So far so good. Any questions on the OAM? We kind of covered 3 topics, the MPLS, LSP ping, the proxy, and then the last one is the connectivity verification using the BFD.
That's all the OEM stuff's way out there, right?
Well, yeah, see, I gave you guys a hint, afterthought. Yeah. So it will come eventually. It will be there, but it's there in the sense standardization. It's happening and it has matured. Eventually they become RFCs. But in terms of the concepts, in terms of what I kind of covered here, that's what it is. So nothing will be changing. And I think we have about 10 more minutes. Hopefully I'll try to wrap it up. This is the last topic, guys. I think we took some questions in between too, so hopefully we are doing okay. The idea here is of the last topic to kind of take what we have covered and give some applicability. Is that right? So the one applicability is the PIM SSM transit. Means if I have an existing MPLS core and if I have a PIM domains, I can do it. And that's exactly what this particular picture is referring to. I got some PIM domain somewhere here at the bottom and up, and then I have an MPLS core. Then the existing MPLS core can be used without PIM running. Is that right? And here I can use a point-to-multipoint TE, or I can use MLDP. Again, I'm not advocating either one. I'm just leaving it at a very high level in terms of the applicability, which protocol to use. But I gave you guys enough hints in the sense of the kind of the deployment where if I have enough receivers, a lot of receivers changing versus if I have a static set of receivers, which is more applicable. But in this example, either one can work. And in the previous session, you have seen that LIF, I guess, which is logical interface that sets up with the RPF checks and all that. But that's all that happens here. And as the last bullet says here, useful usually when there is a need of carrying IP multicast over MPLS, where you have a requirement for MPLS encapsulation, whatever the case may be. For existing provider, if I want to use without the PIN in the core. The other one is MVPN over MLDP, and I think this is the most deployed version. I guess MVPN with Rosendraft, everybody's familiar with the GRE and all that, and it has a concept called a default MDT, data MDT. The same thing here, like in the Rosendraft, you have a group address concept. If you guys have played with it, group address you configure. Instead here you have a VPN ID. Okay, and then it is actually has pretty much widely deployed, pretty successful, with their existing GRE-based Rosendraft. But the thing is, you have to have the PIM running on the P devices, so you don't have to have it with this. And in fact, actually, there is a new draft that he actually becoming an RFC, which incorporates all other mechanisms. It's not only GRE, but you can have these also. So there is a new draft. Actually will become an RFC, hopefully, but yeah. So the two models is the default MDT the default MDT versus the data MDT. The default MDT is where, when you have an initial stream that is set up, it's more like a broadcast where everybody to everybody, like a bus architecture, I guess. And the opaque value that we kind of talked, as part of the FEC element, you have the opaque value. That opaque value will have, whether it's a PIM-SSM transit example we talked about it, which is S, G, or if it is a MVPN, you have a VPN ID MDT number, okay? That identifies. For the default MDT or the data MDT, the MDT number identifies. If I have MDT number 0, for example, that's a default MDT, and any non-zero number is data MDT, okay? The other applicability is the video example as part of some of the drivers or the motivations we looked at it initially at the beginning. And I think I would probably take a bet on this now, and I can say this is more applicable for point-to-multipoint TE, and because we are seeing some evidence now in terms of video content providers and satellite providers and whatnot, kind of taking this lead, and taking point-to-multipoint TE as a deployment. So this is an example of, a typical example of a point-to-multipoint TE for video distribution is you may have a video sender and then a receiver. I can have one unique path and try to replicate only as I get to as close as to the receivers and then do the replication. That's one model. The other model is, as you see here, I got two LSPs set up, one acting as a primary and then the other acting as a backup. So again, just to give different ways of doing it. Currently, there are two ways of doing it. Kind of the second model gives us the path diversity. I think the FRR is the other section we haven't touched so far. So the FRR would be used, like for MPLS traffic engineering, FRR, unicast. It could be that if I have MLDP LSPs can also be protected using FRR. So that's the second or the third bullet that I'm saying. MLDP supports the FRR using RSVP TE unicast, and FRR protection can be used for MLDP. That you don't have to, basically they can coexist together. And we kind of went through and over like which one is better, is it right, in terms of applicability. So depends upon what applications need you may have, and we kind of looked at one of the applications like a video, an example, kind of leaning towards point-to-multipoint TE, and we looked at MVPN, kind of leaning towards MLDP. So pick the right protocol which suits the requirements. I didn't want to go more than that on this particular slide. So we will that's whatever the application requirement would be the case. So in summary, we kind of covered at the beginning what is both point-to-multipoint and MLDP. We looked at how the signaling kind of works for both the protocols, and looked at a little bit of the OAM and some applications. Any questions, guys? Does it helpful? Good. Thank you very much.